Hi, my name is Joseph Gonzalez. I am one of the instructors for Data 100, and I'm also one of the faculty in the ECS department, where I do research at the intersection of AI and systems. And so my research directly connects with the data science curriculum, and so I had the opportunity and the honor to work on the creation of the Data 100 class and teaching over 4 semesters. And so today what I want to talk a bit about is how we created the class, the kind of principles and goals behind it, the sort of students that are taking the class, and then one of my TAs from the last semester and one of the instructors this summer, Suraj, will talk a bit more about the details of the content in the class, as well as how we've adapted to teaching remotely, and some of the new mechanisms we use to teach the material. So I want to first talk a bit about the students in the class. So it's Data 100 is a class with a pretty diverse background. It's also become a very big class. It wasn't always that way. When we first started teaching the class, there were just 97 students, and there were 4 instructors, and among all 4 of us, we were trying to develop content on the fly. It was a challenging and exciting times. And then every semester, or at least the next 2 semesters when I was teaching, after that, we then doubled the class each semester, trying to bring in more students, and then also adapt the content to the changing set of students, as well as the changing world in which the content lives. So I'll talk a bit about the content in a moment, but the class has grown pretty steadily since then. And when I got a chance to teach it again last in the spring, it was the first upper division class to break over 1,000 students. And so our first lecture was in this giant Zellerbach Hall, where the opera goes, famous dances take place. I got to stand on that stage and teach data science to over 1,000 students. So it's pretty exciting. It's a very big class. It's also a pretty diverse class in terms of the backgrounds of students. So first, if we look at the year of progression in their time at Berkeley, we actually tend to be a little more skewed to the second and third year students. This is a class that, after you've taken Data 8, so it's a mezzanine class, but before you might go on to take some more advanced machine learning, statistics, or computer science class. So majority of students kind of second or third year. We also have some graduate students. There's a 200 version of the class which incorporates additional project that relates to something that the graduate students would be doing in their PhD or master's studies. And that version of the class is also helping those students apply hopefully the techniques in the class to their work, their research. We also have a pretty diverse set of students. Over 43% of the students self-identify as female, so in terms of at least gender diversity, it is better than the rest of CS, and something that will hopefully continue to improve and also hopefully improve the diversity of CS as a whole. The backgrounds of students is also pretty neat. So as you'd expect, a large number of the students are declared data science majors or computer science majors, but there are also a number of students in economics, statistics, and then other, where other can be law, the humanities, social sciences, biology, basically across the entire campus. In fact, when I made earlier versions of this bar chart where I tried to include all the majors, the bars are hard to see. So there's many different backgrounds that students come from when they enter this class. All right, so that's a bit about the students. Now, the class is organized, as I said, as a mezzanine class. So it fits sort of in the middle of the data science curriculum at Berkeley. So the lowest part of this chart here is, these are the introductory classes. Data 8 sort of build the foundations that you need to take Data 100. Then Data 100 sits here in the middle that's supposed to prepare students for these upper division classes in statistics, machine learning, computer science. And as a consequence, one of the requirements, the goals of this class is to make sure students have the necessary background to do well in these more challenging classes. But also one of the things that we wanted to do is be able to make this a terminal class. So people who are minoring data science, this might be the last data science class they take. So we need to teach the tools and the techniques, the concepts that would then allow them to take the ideas from this class and immediately start to apply them in their lives and in their future careers. So prerequisites are often a challenge for classes at this scale. Students with a wide range of backgrounds may not have taken these, the classes that we'd like them to take. So what we try to do is keep the prerequisites for this class as minimal as possible and organize them around themes so that students who maybe didn't take the class we had in mind can identify classes that might fulfill that prereq. So if we look at the first prereq here, this is the Data 8 prereq, which is basically having some foundation in data-centric thinking, and so some background in doing basic data science. Then we have a programming prereq, which builds on what you would have needed in Data 8. So it's we need a bit more programming skills, more familiarity with Python, in particular with debugging real-world scripts, code. And so we have a CS61A is a major CS class that a lot of undergrads take, so that's one of the options. And then CS88 is an extension that you can take on top of Data 8. And then finally, we needed some mathematical background. We don't rely too heavily on linear algebra, but we do need familiarity with working with matrices and really basic ideas around eigenvectors. And so we do currently have a linear algebra prereq. Not all students have the background and they can go on and read material online. We try to provide links for any of the prereqs, any of the points in the class where we reference prereqs so students can go teach themselves if they haven't taken the class already. All right, so to design Data 100, we organized it around sort of 3 big goals and the data science lifecycle. So let me first talk about the goals. So the first goal was that we needed to prepare students for the upper division classes, which meant they need to get the concepts that would allow them to bridge from what they learned in Data 8 to taking an advanced machine learning class. And so there's an emphasis on making sure that we had this sort of intermediate set of concepts that we could link ideas in Data 8 to the more advanced ideas you would see in other classes. So preparing students for upper division classes, that was one goal. The other goal, and this one was maybe one of the bigger challenges in the design of this class, is we wanted to enable students to be able to take what they've learned in this class and then go out and use it in the real world. We had to imagine and sort of realize that this might be the last class that they take in data science at Berkeley. And so as a consequence, we need to make sure that we covered real tools and technologies, worked with real data, so they had a chance to think about computation at scale. And that presents challenges when these tools are constantly evolving and they're not well designed for being taught. So this is one of the challenging goals, but one of the important goals of the class. And then finally, we wanted to empower students. So we tried to make it so that the class wasn't really about kind of textbook data sets and classic textbook problems, but about data and problems that students face today. So we work with Twitter. So we try to work with real world data around tweets around politics. We work with food safety, policing in the city of Berkeley. So trying to connect to things that are in students' lives so that they can appreciate the concepts through the problems that mean something to them. They're important to them. All right, and then we use the data science lifecycle as an organizing concept. The data science lifecycle really is a way to frame how you go through the process of data science. It typically starts with either asking a question and then collecting data, or in some cases you start with some data and then try to understand that data. When we start the class, we think about what are important questions that one could ask, what makes a good question, and then how do you go to collect data that can try to answer that question, how does sampling play in that process. Once you obtain the data, we talk a bit about exploratory data analysis, data cleaning, the tools that you would use to go through that process. We actually spent a fair amount of time on that process of going to understand your data, which is really a descriptive process that's not focused on understanding the world yet, but just understanding what you have in the data in front of you. And then we spent a large part of the class talking about how to go from understanding the data to understanding the world, this process of generalization. We bring in machine learning concepts, we bring in statistical concepts. This tends to be a bit more. The second half of the class can be more challenging for a lot of the students because it goes beyond just writing code, and it goes beyond building plots, but through actually making predictions. All right, so we spent a bit of time on understanding the world, and then in the assignments and in the real world, often as you start to understand something better, you start with a simple model, you refine the questions that you ask, you maybe collect or transform the process in which you obtain your data, and then you repeat this cycle. So we use this as an organizing tool to kind of connect the concepts that we covered in the class. All right, so that's a high-level picture of what we're doing in Data 100. Now Suraj will take over and talk a bit about the details of how we're delivering this material and some of the content in that class. Thank you.
Hi everyone, my name is Suraj Rampure, and what I want to now do is talk to you about what exactly it is Data 100 teaches and how we go about doing that. I like to think of the course as consisting of two disjoint but very closely related halves, and that first half consists of practical tools, and the second half consists of modeling and machine learning. In the first half, where we talk to students about practical tools, the first thing we teach students is how to use pandas. And so this directly builds off of the data science library that they learned how to use in Data 8, but there's a lot less hand-holding. So there are a lot of times where we tell students to search on the internet for how to use certain methods as opposed to telling them how to do that in the assignment or in lecture. And that, in and of itself, is an important learning experience. We also teach students how to use SQL as a means of querying from large data sets. And we also teach students how to work with real-world messy data. And part of that is, exploring the columns and filling in missing values. Part of that is also learning how to use regular expressions as a means to extract information from messy data. We also teach students how to use various visualization libraries. Primarily, that has been Matplotlib and Seaborn, but in recent semesters, we have also started introducing various plots in Plotly in assignments and lecture. We also try and train students to discern between bad visualizations and good visualizations, and we try and instill in them this philosophy of making visualizations that are simple and to the point, and that convey the message that you are hoping that it conveys. We also, in the visualization section, teach students how to transform data that might not look linear in order to make it look linear, and also we teach them kernel density estimates as a means of creating smooth estimates of the distributions that data is drawn from. We also teach students in some semesters big data techniques like MapReduce and Spark and various web technologies, though in recent semesters that hasn't been emphasized as much. I like to think of the second half of the course, modeling and machine learning, as consisting of 3 parts itself. We start off by reviewing various types of samples and how to compute probabilities related to those samples, as was done in Data 8. We also introduce this idea of a random variable, which will be more useful later on when we talk about the bias variance trade-off, and we talk about various properties of random variables. We also introduce this idea of a modeling recipe, where we teach students what exactly a model is and how to choose the optimal parameters for your model. And that involves choosing your model, choosing a loss function that you want to evaluate your model with respect to, and then minimizing your loss function averaged across your entire data set. And this is a series of steps that will repeat itself throughout all of the models that we teach students. We also review the simple linear regression model that was introduced to students in Data 8. After the simple linear regression model, we generalize to the ordinary least squares model and derive that using a geometric argument. And from there, we generalize in all possible ways that one typically does when studying regression. So we talk about feature engineering, we talk about regularization, and this idea of the bias variance trade-off, which is where probability and random variables reappear. We talk about cross-validation, and these sort of all serve to build upon the simple linear regression model that they originally saw in Data 8. We then talk about this idea of gradient descent. For the most part, up until this point in the class, students have used inbuilt techniques like scikit-learn's model.fit to abstract away the process of determining the optimal parameters for a model, but we think it's important for students to understand how gradient descent itself works, and so in the assignments that we have for gradient descent, students implement it by hand for various models. We then step back from this idea of regression and introduce this idea of classification, where we now want to predict a 1 or a 0, and we talk about how we can adapt our linear regression model for doing that, and that, of course, is logistic regression. We wrap up the course by introducing students to decision trees and random forests, which we present as being an alternative technique for both regression and classification, and we also introduce students to a few ideas in unsupervised machine learning, such as principal component analysis and clustering. Throughout the entire course, we teach students both the theory behind these techniques, but also how to use them in practice on real-world datasets with tools such as scikit-learn. And these are just a few examples of the real-world tools that we teach students how to use in this course that they will then use later on in their future research and careers. What I wanted to now do is show you a few examples of assignments in Data 100. This first one has students analyze Twitter data from Donald Trump, and this one in particular is a favorite of both students and staff. In this assignment, students wrangle with messy data and work on getting it into a format that's easy to work with in Pandas. And after they do that, they create several visualizations about that data. So for example, they create a visualization about the various devices that tweets were made on. They create visualizations about the different sentiments in tweets talking about different news sources. And in this assignment, we also have students think about how exactly the tools that they're using work. And so one example question we ask them is, are there times where Vader, which is a sentiment analysis technique, works well, and are there times where it doesn't work so well? And so we have students think about these sorts of things and write out sentences instead of just writing out code. And we have our tutors grade these answers to make sure that it's not all just passing autograder tests. Another assignment, which we administer towards the end of the course, has students build a logistic regression classifier to predict whether emails are spam or ham, where ham is not spam. And in this assignment, we have students first explore the data that they are given, and then we scaffold them to build a basic logistic regression model that reaches a 75% classification accuracy, and then we leave it open to them to build the best possible logistic regression model that they can. And we hide some of the test set and have them submit to Kaggle in order to evaluate their model on this hidden test set. And students really love this assignment because it's quite open-ended towards the end. They're kind of on their own and have to build the best model that they can in whatever way possible. The final assignment I wanted to show you involves gradient descent. So we start off the assignment by having students implement derivatives on their own and using these derivatives to implement gradient descent on some model that we specify to them. And we then have students explore how the optimal parameters are found using various versions of gradient descent. So for example, gradient descent with a static learning rate and gradient descent with a decaying learning rate. And you can see here the loss surfaces are visualized, and these pictures really help students understand what is going on when we, for instance, implement a decaying learning rate. Students access all of these assignments by going to our course website, which is linked at ds100.org. And on that website, you can click to see the websites for every specific semester. And so the summer one is ds100.org/su20. Assignment links on this page redirect students to their own Data Hub container, and in those Data Hub containers, assignments are pulled from our public GitHub repo. And all assignments and lecture code are publicly hosted at this repo so that students who don't have access to the Berkeley domain can access these assignments as well. In order to supplement the assignments and lecture material, we also have a textbook that was written specifically for this course, which is linked at textbook.ds100.org, and it serves as a really nice supplement to the lecture content, and it is constantly being worked on and refined. Here's an example syllabus for the course. As you can see, there is a little bit of flexibility in when topics are presented. Here, each row corresponds to one lecture, and in a typical fall or spring semester, there are 2 lectures per week. As you can see here, most of the toolsy content, so that's SQL, Pandas, regex, visualization, all appear together towards the beginning of the course, and most of the modeling content comes afterwards. What I now want to do is talk about how the course is run. Each week, usually, there is a homework assignment that tests a core concept. And these homework assignments, as I demonstrated earlier, consists of both an auto-graded component and also a written component that is manually graded by our tutors. The weeks that we don't have a homework, we instead have a project, which is sort of like a 2-week-long homework that revolves around some central data set. So for example, analyzing the sentiment in Trump tweets, or building a logistic regression classifier, or predicting house prices in Ames, Iowa. These are the sorts of data sets that we make projects out of, and they test multiple ideas. Each week, there's also a lab assignment that is designed to introduce students to a new idea, and these are typically supplemented with an in-person live lab section, which I will talk about in just a minute. Also typically part of a student's grade are vitamin assignments, which are meant to be quick 10-minute multiple choice quizzes that students take each week on an online platform such as Gradescope, meant to ensure that they're keeping up with the lecture material. We also, depending on the semester, have 1 or 2 midterms and a final exam. Let's talk about what a typical week looks like for students in our course. There are 3 hours of lecture, So we have 2 90-minute lectures a week in a fall or spring semester. There's also 1 hour of lab section each week where students work together with other students on that week's lab assignment, and they also get help from course staff that are at the lab. There's also an hour of discussion section each week where TAs recap the core concepts from lecture from the past week and students work on problems together in groups. And there are also several hours of office hours from Monday through Friday where students can come and work with other students and get help from staff on the assignments for that week and concepts from lecture as well. Let's talk about staffing. In a course with over 1,000 students, we have a pretty big staff in order to make sure that we can adequately support the students that we have in our course. Normally, there are 2 instructors, one from the CS department and one from the statistics department. We also have roughly around 30 teaching assistants whose formal title is graduate student instructor. Roughly 2/3 of them have 8-hour-a-week appointments, and they spend the majority of their time teaching discussion section, lab section, and office hours. About 1/3 of our GSIs have 20-hour-a-week appointments, and in addition to teaching, they also spend their time helping develop course content and manage logistics and infrastructure, and generally just making sure that the course runs. In addition to teaching assistants, we also have roughly 20 tutors that primarily help with grading and assist in office hours, and in some semesters they also facilitate small group tutoring sections, and these allow students to work with other students in groups of around 6, as opposed to discussion sections and lab sections, which can be up to 30 students in size. We also have a variable number of academic interns whose formal title used to be lab assistants, and academic interns help in office hours in exchange for academic units. And we are trying to build this pipeline of students becoming academic interns and then becoming tutors and then becoming teaching assistants, building experience along the way. This presentation wouldn't be complete without talking about our adaptation to remote instruction due to COVID-19. The biggest change in how we are delivering content to students is that lectures are pre-recorded instead of being live. Each lecture is broken into a series of short videos with conceptual questions in between to ensure that students are actively learning instead of just passively learning. We will also be hosting supplementary live lecture recap sessions in order to recap the concepts that were presented in the pre-recorded lectures and serve as a way for students to interact with the instructors. In the physical instruction setting, office hours and lab sections for our course already ran pretty similarly. Students would join or come to the room and put their name on some queue, and when it was their turn, someone would come and help them. And so we've decided to merge office hours and lab sections in the remote setting. And so now students will log on to a website, put their name down and what assignment they need help with, and once it's their turn, they're called off the queue and put into a Zoom call with a staff member who will help them with whatever they need help with. Discussion sections are what we really are experimenting with the most. We plan on having 2 modes for students to interact with discussions in. One mode is to watch a pre-recorded discussion video and then come to office hours to talk about the concepts that were in that discussion. And another mode is to host more traditional live discussion sections over Zoom where students can come and interact with other students and TAs in a more synchronous fashion. Here are 2 examples of how we have thought of presenting lecture material. On the left is an example of a lecture from Spring 20, where the lecture consists of a notebook with code in between and videos and questions embedded in it. On the right is a format that we may experiment with over the summer, where each lecture has a single web page and a bunch of embedded videos. These are currently just placeholders, and the code and conceptual questions are linked off to the side. And we plan on doing these in Google Forms so that we can track how students are answering these conceptual questions. I believe that's all we have for today. Don't hesitate to reach out to either Joey or me with any questions, and thank you for listening.